Namaste and welcome to this course on mathematical foundations for machine learning. We have been looking at very interesting things as far as this part of the course is concerned, like we are looking at linear algebra, and we started off the first week with the idea of vector spaces, fields, vector spaces, then the various operations that you can do on vector spaces. We just looked at the idea of subspaces, then we looked at basis, dimension and so on. And then in the next week we followed it up with what are the things that you can do on a vector space, like we basically looking at linear transformations, and we looked at a lot of linear transformations and stuff. We also looked at those stubborn vectors for a linear transformation which do not get reoriented. We said that look, it just gets scaled. These are like those stubborn fellows that you have, like whatever you try to do, it does not change this direction or orientation. So we have had the idea of eigenvalues and eigenvectors, and then we said that in the subsequent week we started off with the idea of orthogonality, and we figured out what it is to say orthogonality. We said that okay, we wanted to bring in another operation onto the vector space which we called as the inner product or the dot product. And then we said that we could also get some idea about the angle between the two vectors. We could bring that also as a part of our definition or the mathematical expression for the dot product or the inner product. And then we said that if the dot product is 0, then we said that the angle between the two guys or the two vectors is going to be 90 degrees or perpendicular, or the vectors are said to be orthogonal to each other. And we also looked at more powerful idea of or applications of orthogonality in terms of orthonormal basis for a vector space, where given a vector space you could actually pick orthonormal vectors and you can express this any vector there in that vector space as a linear combination of these orthonormal vectors, and it was easy to get the scalars in that case, right. It was very easy to get the dot product, just take the dot product of vector with every vector in the basis, and then you say okay fine, since they are orthonormal you get the coefficients very easily. And in fact basis expansion in terms of orthonormal basis was actually called the Fourier expansion. We also did a little bit of the Parseval's identity and so on. And we concluded the previous class with questions on orthogonal projections. Given a set of linearly independent vectors, can we get orthogonal vectors? That is where we said we will look at the idea of Gram-Schmidt orthonormalization and QR decomposition, and we also said this orthonormal or orthogonal transformations, they preserve length. And then we said that we will look at real symmetric matrices. Real symmetric matrices, as far as machine learning is concerned, has a very significant application and stuff. In fact, I keep saying that the variance covariance matrix that you have is basically a real symmetric matrix. So now in this lecture what we will do is we will look at the idea of orthogonal projections, and we will say why these projections are important, what is it that you get out of projecting a vector onto another vector, and then look at the idea of generating orthogonal vectors using Gram-Schmidt orthonormalization process, and we will also look at the idea of QR decomposition. So let us get on. We are going to look at orthogonal projections now. So orthogonal projections. So what do we mean by orthogonal projection? So what I am going to do is I am going to assume that I have a vector space V, and this vector space V is also equipped with the inner product operation, because without this inner product operation it is impossible to look at orthogonality and stuff. So what I am going to do is I am going to look at vector space V. Let V be an inner product vector space. So by the very meaning of saying inner product vector space, we refer that we say that okay, the vector space is equipped with inner product operation. So, we are going to say let V be an inner product vector space and we are going to consider let us say u be a non-zero vector, u be a non-zero vector in V. Let us also consider another vector, let V be another say non-zero vector in V. So, I am going to look at something like this. How is it going to look like? So, I am going to say that look, I have this vector which you call it as let us say V, and I have another vector which is basically u, and the angle between these two guys let it be say some theta, right. Now, I have this. Now, what I am going to say is I am going to find out what is the shadow of this guy V, what is the shadow of this guy V in the direction of u. Now, essentially what I am asking, I am asking what is the amount of information of V that is present in the direction of u, right. If I say that look, there is some amount of information of the vector V that you can find in the direction of u, I am just going to find out what is that amount of information which is present in the direction of u of that of the vector V. So, basically as I said, I am going to try to find out what is the shadow of V in the direction of u, right. So, how do we find it? What is it that we are going to have? So, that is basically the crux of this lecture. So, what is the information of V available in the direction of u? In the direction of u, right. So, how do we find this out? Okay. So, we can do it see essentially what we are trying to say is I just want to okay, let me also put it this way. So, the other way of looking at it is we want to decompose, we want to express or decompose the vector V as let us say V is equal to say some k u plus let us say u will give this notation u perpendicular, right. What does this mean? So, this is going to be my u perpendicular and this is going to be k u. Now, let me put this as v perpendicular. Okay. Let us take this as v perpendicular and change this here v perpendicular k u plus v perpendicular, right. So, what are we trying to say? We are going to say that since we already have the idea of the orthogonal complement vector space, what we are going to do is we are going to look at the following. So, we have this vector V which is going to be k u plus v perpendicular where V perpendicular is an element of the orthogonal complement of the orthogonal complement subspace to the subspace containing the u vector. Right, this is what we have. Okay, so how are we going to do it? Let us take this up. Okay, so essentially what have we asked for? We had a vector v, and this vector v I am going to write this as ku plus v perpendicular. So, we said that this v perpendicular is going to be orthogonal to the vector space that contains ku, right. So, let us do that. So, the question is like what is this k? Basically the factor that we want, that is basically the amount of information of v that is available in the direction of u. So, that is what we are going to find out. So, k is some real scalar, right. Now, from the figure what we see is, we see that okay, we had this vector to be the vector v, and we said that this is the vector u, this is the angle theta, and we said that okay, this is the perpendicular that is dropped and this is basically perpendicular. So, what we have is we have v perpendicular, the component that we have is orthogonal to u vector. But what is v perpendicular? V perpendicular is nothing but the vector v minus the vector which is basically ku, right. The vector v perpendicular is basically the vector v minus ku. So, what I am going to do is I am going to say v, the vector v minus ku dot product with u is basically 0, right. Basically this is the component which is nothing but v vector minus ku, right. So, what we have? We have v dot u minus k u dot u is equal to 0, that is a scalar there. So, what we have? We have k is equal to v dot u divided by u dot u, right. So, that is the scalar that we have here. So, what is the amount of information that is present in the direction of u of v? It is basically k u, which is nothing but v dot u divided by u dot u in the direction of u, right. This is the basically this is what we call as the projection of the vector v in the direction of u. This is basically the projection of v in the direction of u. In fact, this is also the orthogonal projection. So, let us write that this is basically the orthogonal projection of v in the direction of u, or putting it in another better manner, we say that this is the orthogonal projection of V along the direction of U. Along the direction of U. Okay. So, let us look at something interesting here. Let us take up this. So, just take a simple example. We will look at this example. Example, we have this B vector which is basically let us say 2 3, and U vector is basically let us say the 1 0 vector, which is basically your normal unit vector along the x1 axis in R2. So, basically I am going to look at two vectors which are there in R2, where I want to look at the projection of V along the direction of U. So, how is this going to be? It is going to look something like this. I have my 1 0 axis, basically let us call this as the point 1 0, and I have my vector which is 2 3. So, basically okay, let us do this. So, my x1 axis is this, x2 axis is this, I have 0 here, 1 2 3 4, and I have 1 2 3 4 here. So, the vector that I have is basically 2 3, 2 3 is basically somewhere here. So, this is the vector 2 3, and I want to look at the projection of 2 3 along the direction of 1 0, which means I am going to look at something here. So, 1 0 vector is here. So, I can take multiple of this 1 0 which is going to be here. So, along this direction of 1 0 is basically what I want, right. So, how do I get this projection? We already have seen the expression for projection. So, we say that projection of V in the direction of U is nothing but V dot U divided by U dot U in the direction of U. So, V dot U is nothing but, we already know how to find out the dot product of two vectors. So, I am going to take this 2 3 this way, and then the 1 0 vector which is this divided by U dot U, which is going to be 1 0 dot product with itself in the direction of 1 0. So, this is basically the vector 2 0, right. 2 into 1 is 2 plus 3 into 0 is 0, then divided by the unit, this is a unit vector. So, the length is going to be 1. So, I am going to have 2 into 1 0. So, this is going to be the projection is going to be here, this guy is going to be the projection of that vector. So, if you look at this guy is going to be the projection of that vector along the direction of, so this is the 2 3 vector that we had along the direction of 1 0, right. Now, let us look at this projection formula a little bit more in a different manner. Let us look at that right now. So, what did we say? We say that okay, projection of U or V along the direction of U is V dot U divided by U dot U. So, let us take this again. Projection of V along the direction of U is nothing but V dot U divided by U dot U in the direction of U, which is the same as, I can write this as okay, V transpose U divided by U transpose U in the direction of U, right. It is in the direction of U, right. Now, I can actually, since I know that the dot product is commutative, the operation is commutative, that means V transpose U is the same as U transpose V. So, I am going to write this as U transpose V divided by U transpose U in the direction of U, right. So, this is going to be the projection of V in the direction of U. This is what we have, right. Now let us see if we can make, now if you look at this, something interesting happens. Now this guy is basically a scalar, this is the scalar and this fellow is the vector that we have here. So what I am going to do is I am just going to do a small realignment here or readjustment here. So I am going to write this as u, the vector u, into u transpose v divided by u transpose u. This is what I am going to write. This is going to be projection of v along the direction of u, right. Now I am going to do a further step here. I am going to write this as u transpose divided by u transpose u, and then I am going to write this v vector here. So this is basically the projection of v along the direction of u. See, basically what I have done is a scalar multiplying a vector. Now what I do is this scalar, I mean whether you put it in the front or after this, it is not going to make a big deal because you are just going to do a scalar multiplication of the vector. Now what I do is I am going to reorient or readjust this expression that I have. So what I did is I brought this u here and then I said that instead of writing it as u transpose v divided by u transpose u in the direction of u, what I did is I took this u into u transpose into v divided by u transpose u. Essentially what I did is I again pulled out all this u transpose divided by u transpose u together and then call this and then put that v out. So saying that projection of v along the direction of u. Now what we want to do is we want to figure out what is this term actually, what is the term, let us figure out what that term is. So let us consider this, the vector u in our case let us say it was 1 0. So the u transpose is going to be this 1 0, right. So what is u times u transpose? Now is this operation even allowed? I mean we have to check whether that is possible. Of course it is possible because this u vector is basically a 2 component vector and this u transpose is going to be like a row vector of 2 elements. So I can do this multiplication which is u into u transpose because you get 2 by 1 multiplied with 1 by 2, it is allowed. The number of rows is equal to number of columns here and I mean so the number of columns here is equal to the number of rows here. So that is allowed. So what I do is I basically multiply these two guys. So 1 0 into 1 0, oh this looks like I am taking two different multiples and then I am going to do scalar multiplication with this vector. So I am going to get 1 0 0 0, that is what I am going to get. It is 1 time 1 0, then I will take it as 0 times 1 0, 0 times 1 0. So what am I going to get? I am going to get 1 0 0 0. Oh, that is pretty interesting because we ended up getting a matrix here. We have got a matrix here. We were trying to do the scalar I mean the dot product where we were talking about scalars and stuff, and suddenly what we did is we just took u into u transpose, that resulted in a matrix. And remember u transpose u is basically a number. U transpose u is this into that. So I am going to get 1. This is a number. This is a scalar. The inner product is basically a scalar, and when you write u transpose you basically call this as the outer product of vectors. This is called the outer product. Outer product of vectors, and outer product of vectors, what did it give us? It gave us a matrix, and that is pretty interesting. So what we have is basically a matrix here. Right, this is a matrix and this is going to be a 2 by 2 matrix for in this case where 2 by 2 matrix, since u is an element of R2, right, u is an element of R2, u transpose gave me a 2 by 2 matrix. Now that is pretty interesting. Now let us figure out some more interesting properties of this u transpose, then we will get some good idea. What is the property? Now let us look at the example that we took, if we take u transpose, let us assume that let us just focus on this, let u be this vector u1 u2, and therefore what is u transpose? U transpose is going to be u1 u2. So, I am just going to play around with 2D vectors or vectors in R2, so that we can understand this better, and then we can use it for any n dimension this is going to work. So, what is u transpose here? U transpose here is basically u1 u2, this vector, and into that u1 u2 row vector, which is essentially saying, look, I have u1 multiple of u1 u2 as the first column, and then I have u2 multiple of u1 u2, right. Oh, that is pretty interesting. Here is a matrix which is say 2 by 2 matrix, here is a 2 by 2 matrix, and we see that both the columns are basically multiples of each other. That means this column of the matrix and this column of the matrix are linearly dependent, right. We see that the u transpose, let us write this again, this is going to be u1 into u1 u2, u2 into u1 u2, right. This is what we have. Now, if we see, let me call this as the matrix P. Now, what do we see here? We see that the columns of P are linearly dependent there are only 2 columns and both the columns are linearly dependent. Therefore, you see that one of the columns is a scalar multiple of the other column, and therefore, we say that P is equal to u transpose has rank 1, right. The column space of P, the column space of P or the range of P is one dimensional subspace of R2. So, the most important statement that we are going to make is the outer product of 2 vectors, outer product of 2 vectors let us not say 2 vectors, let us say outer product of a vector with itself. We will come back to this 2 vectors case a bit later. Outer product of a vector with itself results in a square matrix of rank 1. This is the first comment that we are making about the outer product. The matrix generated as an outer product of a vector with itself, it results in a square matrix and it is of rank 1, right. And in fact, something more coming up. What is that? Let us look at this. We have P is basically, we said this is a rank 1 matrix. Right, P is a rank 1 matrix, we said. Let us look at what is P transpose. P transpose is basically u transpose the whole transpose, right. It is basically u transpose the whole transpose. The matrix is basically obtained as u transpose. So, what we do is we want to do P transpose is u transpose the whole transpose, which is nothing but u transpose the whole transpose into u transpose, that is nothing but u transpose itself. Wow, that is pretty interesting, because this is a matrix which says, look, P transpose is equal to P. What kind of matrices have this property? P transpose is equal to P. What do you call such matrices as? Yes, you call these matrices as symmetric matrices. That means the matrix that you obtained as U transpose, in fact this is basically the projection matrix. So, we are going to say that the projection matrix P is symmetric. That is P transpose is equal to P. Okay. We could actually see that from here also. You could check it here itself, like when you take the multiples, you actually see this is going to be this matrix here, you are going to have U1 squared, this is going to be U1 U2, this is U1 U2, and here you see it is U2 squared. Now, what is interesting is if you take the determinant of this is going to be U1 squared U2 squared minus U1 squared U2 squared, the determinant is 0. Therefore, this is a 2 by 2 matrix with determinant 0, therefore, the rank is going to be 1 for U being a non-zero vector. So, the first understanding that we had was outer product of vectors, the projection matrix was obtained as the outer product of a vector with itself. So, this is what we had. So, this is basically the projection. Now, what we can do is you can take any vector, why should it be just V? So, now what I am going to do is suppose I can actually say this, what is that? All I want to do is if I want to project any vector x in the direction of u, you just do it like a matrix transformation. It is in fact the projection is a matrix transformation that you see here. This is of the form say some a into b. So, you can get some vector here. Is this clear? So, this is basically I can take any vector now along the direction, the projection of the vector along the direction of u is given by u transpose divided by u transpose u. This is a matrix and you have your x vector here. So, I can do this is basically a linear transformation, you can actually prove that this is in fact a linear transformation and so on, right. So, we have this. So, the first property that we studied out of projection matrix is that it is symmetric, and we also figured out that in this case it is a rank deficient matrix. What we had was a 2 by 2 matrix, but the 2 by 2 matrix has rank 1. So, we say that the matrix is rank deficient in this case. Let us look at one more stuff here. So, I mean I did not write the scalar down there which was like u transpose u. I did not do it because u transpose u is basically a scalar. So, we can you can pull that out of the we could do this also. So, we had P to be u transpose divided by u transpose u. So, now I can figure out P transpose is u transpose divided by u transpose u. This is a scalar. So, I can write this as 1 by u transpose u into this is a matrix, we have u transpose, this is the matrix which is the whole transpose I am going to take now, the whole transpose. So, I am going to get 1 by u transpose u, it is a number. So, it will remain as same, nothing changes, and here again this is what we already did, this is going to be u transpose the whole transpose into u transpose, which is nothing but 1 by u transpose u into u transpose. So, we said that P transpose is equal to P itself, right. Interesting. Now, I want to look at one more. What is this one more? I want to find out what is P into P, or what is P into P, which is basically P squared, right. I will write this as P into P, which is basically P squared. I want to find out what is P squared. Let us do that. P squared is nothing but P into P, which is nothing but u transpose u which is nothing but u transpose divided by u transpose u into u transpose divided by u transpose u. This is what we have. Now, if you see here I have u, then I have u transpose u, then I have u transpose divided by u transpose u into u transpose u. This is what I have. Now, the term that I have written in green is going to cancel out with one of these guys, because that is a scalar, this term is a scalar, this is a constant. So, you can pull that scalar out and then you say that okay, that knocks off one of the fellows in the denominator. So, what we have here essentially is u transpose divided by u transpose u. Oh, that is fantastic. What do we have? We have p squared is equal to u transpose u, I mean p squared is equal to p itself, right. That is interesting. So, we call such matrices for which p squared is equal to p, we call these matrices as idempotent matrices. Idempotent matrices. Right, this is called as idempotent matrices. Therefore, what is interesting, we are going to make this statement: a projection matrix is P, a projection matrix P P is A symmetric and B idempotent. So, any matrix which is actually symmetric and idempotent, now we are going to call that as a projection matrix, which means okay, you have a matrix M which is going to be symmetric and idempotent, you call that matrix M as a projection matrix that could project any vector along the direction of say some other vector, right. So, that is always there. Okay. Now, let us try to understand what this idempotent actually means. We know that p squared is equal to p, this implies this is basically p transpose is p and this is p squared is equal to p, right. Now, what is it to say p squared is equal to p? That is something which we need to understand. Let us figure out what it is. So, let us look at this. See, for example, I have my let us say x1 axis and let me say x2 axis I have here, and assume that I have this vector and this vector is projected onto let us say this vector is projected onto the x1 axis. So, this is basically the orthogonal projection of this vector let us say v along the direction of 1 0, right. This is basically this is let us say v1 v2 are the components and I am going to get this as v1 0. That is the orthogonal projection of the vector v along the direction of the vector which is 1 comma 0. Now, what is it to say p squared is equal to p? It simply says that I have a vector v which I projected, right. I got let us say some other vector which is like say v dash. Now, what I am going to do is I am going to apply this projection transformation again on the already projected vector which is nothing but p times v dash, and what it says is look, I am still going to be the same thing that you had which is pv, right. That is what it says. It is like saying I take a big hammer and then hit this arrow on the head, right, hit the vector on the head. So, this vector falls down here, right, the vector basically falls down here in this direction. Now, what I am going to do is the vector is already there on the ground. What I am going to do is I am going to hit with the same hammer on the head of this vector. Where does that vector go? It does not go anywhere else, it will be there in the same direction. So, that is what it means to say p squared is equal to p, right. So, it cannot change in the direction, does not change. So, that is basically what p square is equal to p means, right. The effect of doing this projection twice on the vector is the same as projecting that vector only once in that direction whatever that you are looking for. So, that is basically your projection vector. Is that clear? So, that is basically the properties of some of the projection matrix. I mean, you could even try out something else. So, suppose I give you here is a vector, oh sorry, suppose I tell you that look, here is a vector u which is basically the 1 1 vector. I have this vector 1 1. I want to find out this why 1 1, let us take a different number, let us take 2 1. I want to project any vector x, project any vector x along the direction of u. Along the direction of u, right. Okay. So, I want to figure out what is the matrix that it's going to do. So, what is the matrix? Matrix that projects any vector along the direction of 2 1, right, is basically given by, we already know what it is. What is that? It is u transpose divided by u transpose u, which is nothing but 2 1 2 1 divided by 2 1 2 1. Remember, the inner product and outer product of are two different operations. You cannot cancel out the numerator with the denominator. It is, I mean, it is not correct. U transpose gives a matrix, u transpose u gives a scalar. Okay. Now, what are we going to get here? We are going to get, this is nothing but 2 times 2 1, this is 1 times 2 1 divided by 2 into 2 is 4 plus 1, which is basically 5. So, I am going to have this matrix which is nothing but 4 1 4 2. So, I am going to have this matrix which is 4 2 and 2 1 divided by 5. So, the matrix P which is going to project every vector in this direction is going to be 1 by 5 into 4 2 2 1, right. That is the matrix which is going to project along the direction 2 1. Now, we may also have this question, see what happens to a 3 component vector, like how are we going to get suppose I have a 3 component, or I have a vector in R3, I want to project this any vector along the direction of this vector, say u in R3. Suppose I have u which is an element of R3, right. I want to project. So, let us say I have, which means I have this, I have 3 components, namely u1, u2, u3. Now, I want to project this any vector in the direction of this u vector which is defined as u1, u2, u3. I can still use the same stuff. P is equal to u transpose divided by u transpose u, and this is nothing but u transpose is going to be u1 into u1, u2, u3, u2 into u1, u2, u3, and u3 into u1, u2, u3. So, these are basically the u1, u2, u3 scalar multiple of the same vector u divided by, I am going to have u1 squared plus u2 squared plus u3 squared. This is what I am going to have, right. So, this is precisely what we have as our matrix. So, you can do it for any n dimensional vector. So, this projection matrix is going to be the same, and in the sense u transpose divided by u transpose u and so on, right. So, what we saw now is like we figured out what is that matrix which is going to project every vector in the direction of a given vector. We figured out that, and it turns out that the matrix which is basically a projection matrix was idempotent and symmetric, and it was also a rank deficient matrix that we saw. Now, where do we go from here? We want to figure out, okay, what is it this, I mean, why would we want to project? We said that, okay, we want to find out the information that is available about a vector in the other direction. Now, what is interesting to notice, if you remove this information along the other direction, basically I had this vector u, I mean I had this vector v and I had this vector u. Now, what we did, if you remove this information from v, say this is basically T u I had, if I remove V Tu from V, I am going to get V perpendicular, and what is interesting is I had this vector V and I had this vector U which were linearly independent, they were in two different directions. Now what I am going to see is when I subtracted this fellow, which is basically the amount of information or the projection of that guy V along the direction of U, I ended up getting a vector V perpendicular which is basically orthogonal to U and right, and it is basically orthogonal to U. That means we have removed that amount of information which is available in the direction of U. When we remove that, we get two fellows which are orthogonal, they do not share any information with each other, right. That is brilliant. The shadow of this guy V perpendicular on the in the direction of U is 0, right, because the dot product is going to be 0 here. So that brings us to a very interesting question. Given two linearly independent vectors U and V, is there a way in which I can actually generate vectors which are orthogonal, and that is precisely what we are seeing here. V perpendicular is orthogonal to U, right. V perpendicular is orthogonal to U, and that is the information which was not available there in the direction of U. In fact, we could also say that suppose you take two numbers and then you divide the bigger number by the smaller number. Suppose if both of them are not multiples of each other, you see that there is a remainder which is there, and that remainder is something which is like an error. So for example, I have 27 and then I take this number 5. So when I divide 27 by 5, I can write 27 as 5 into 5 plus 2, and this fellow 2 is basically like the error that you have, right. That is precisely what my V perpendicular here is. So the question is, can I use this process to generate orthogonal vectors, and that is what we will see in the next class as Gram-Schmidt orthonormalization process or orthogonal processes, right. So the focus of the next class is going to be Gram-Schmidt orthogonalization algorithm or technique or process, right. We will do that. Namaste.